Hello, y'all. Welcome to lesson 123 of my DP chemistry curriculum. Today we're going over reactivity 3.3.1 and 2, which is talking about radicals. And a radical is a molecular entity that has an unpaired electron. Radicals are highly reactive, so we'll go over that. And we'll be able to identify and represent radicals such as like methane radical and chlorine radical. Furthermore, we're going over 3.3.2, which is how radicals are produced by homolytic fission. This is either going to be like halogens in the presence of ultraviolet light or heat, as well as chlorofluorocarbons and such. We'll explain, including equations, the homolytic fission of halogens, known as the initiation step in a chain reaction. So we're going to look at a little bit of that chain reaction as demonstrated through chlorofluorocarbons and the ozone layer. So with that said, let's go right into it. Let's repeat what radicals are. Make sure that we have that definition down, which is just a reactive species with one unpaired electron. Now, this species could be an intermediate or the end step of a process, but we're going to go over how we identify them and how they're created. So one of the things to think about is when we look at like Lewis diagrams of like chlorine or maybe fluorine, mostly our halogens we're going to be referring to a lot, bromine. You'll notice that we always have paired electrons. I use the lines to represent two electrons. Uh, we never really have that unpaired electron. We never just have like a chlorine with 1, 2, 3, 4, 5, 6, 7 electrons as such. We know that the diatomic elements never do. They don't exist in this state. They instead form bonds and form these covalent compounds because the unpaired electron is very reactive. An unpaired electron is very reactive, meaning that a species that has an unpaired electron doesn't last long in the environment. It almost immediately goes ahead and reacts with something. What they try to do is they tend to form a more stable covalent bond. With an electron from another substance. So they're just going to go ahead and try and pair up that electron by making these bonds. So what do these radicals look like? How do we represent them? Well, to represent a radical, it's very simple. We literally just represent the unpaired electron. There's a chlorine radical with an unpaired electron. Uh, OH with an unpaired electron. We could do an O2 minus with an unpaired electron, CH3. And so these are all examples of radicals. So as we go through this, we're going to be representing these radicals in chemical equations. So you need to be comfortable using these as such. Now, for this section, however, we're mostly going to just be referencing our halogen radicals, but we'll have a couple others as well. So how do we form these? Well, this is formed through what we call homolytic fission. If we break this up, homo means same, lytic means to break. So homolytic fission is going to be the breaking of a bond, specifically the breaking of a covalent bond where each atom gets one electron. So it's the same because they each get one electron instead of both electrons moving to one or the other, like how we might form ions when these things bond, where both electrons go over to one and one electron stays with the other. For example, like when we looked at acids and bases, HOH, water can break down into H plus OH minus, where both electrons move off the or the electrons in the bond both move onto the oxygen. And so in homolytic fission, it's more even. So this is not homolytic fission. An example might be where we have chlorine and chlorine, and they form Cl radicals, two chlorine radicals. So this is homolytic fission. This is not. So that's where we get that idea. Now, what actually causes homolytic fission? A very common thing is actually ultraviolet radiation. So UV rays can break some covalent bonds. Now, what does need to happen is they need to have low enough bond enthalpy. So oxygen, diatomic oxygen, is a double bond with very high bond enthalpy. Ultraviolet can't break that. But something like a chlorine-chlorine bond, most of the halogens can be broken via that UV radiation. You'll notice that actually in this example right here, we made two radicals. So one of the things that the DP requires you to be able to do is actually show this process. So how do we show the process of radicals being formed? Well, we use what's called a reaction mechanism. A reaction mechanism is basically a detailed method to show elementary steps, being the simplest steps of a chemical reaction. We go over that in the HL curriculum, but mostly you just need to know that it is a detailed method to show this chemical reaction. Within a reaction mechanism, we are going to use one-sided arrows, sometimes called fishhook arrows, to demonstrate the movement of one electron. So let's go ahead and use the reaction mechanism to represent the homolytic fission that I drew above. So how do we actually do this with a reaction mechanism? Well, we take our chlorine, bonded to chlorine, and it starts pretty much the same with ultraviolet radiation. But what we're going to do is now show that the two electrons in the bonds move one over to each chlorine. You'll notice I use these arrows, which kind of look like fish hooks. They only have one side to them, meaning they don't have two sides to them. And this shows the movement of one electron. What ends up being our result is one chlorine radical plus another chlorine radical. You'll notice that I put the two electrons on opposite ends. This doesn't matter so much. They both refer to the same compound. So that's how we can demonstrate homolytic fission, creating the radicals using a reaction mechanism. So as we continue this discussion of radicals, what we're going to do is we're actually going to refer to chlorofluorocarbons. So we're going to observe CFCs. These are chlorofluorocarbons. Knowing a little bit from our previous units, chlorofluorocarbons must be halogenoalkanes, in which we have a chlorine and a fluorine bonded to a carbon. So what we're going to do is actually look at a couple properties of these. So if we look at the carbon-fluorine bond and the carbon-chlorine bond, we'll notice that they have a bond length of 138 and 177 picometers respectively. So you'll notice the carbon-fluorine bond is smaller. You can probably predict that due to the higher electronegativity in the fluorine. Furthermore, if we look at enthalpy, with a smaller length and higher electronegativity, you can assume correctly that fluorine would have a higher bond enthalpy, having 492 kilojoules per mole. Meanwhile, the chlorine only has 324 kilojoules per mole. So from these observations, we can assume that chlorine is more likely to become a radical. So we can see the reactions that will happen due to this. One of the really important things about talking about radicals in terms of chlorofluorocarbons is that these are actually now banned because they were creating holes in our ozone layer. So how do they actually do that? Well, we're going to see through the process of radicals and why it's so important to not have these compounds in our atmosphere. So let's go ahead and look at what will happen to this bond when exposed to UV. So here we have a simple chlorofluorocarbon, and in the presence of ultraviolet radiation in our atmosphere as this gets released, we see that the bond between the chlorine and the carbon will break, causing us to create a radical, specifically two radicals. So right now we're going to focus on the chlorine radical. So let's go ahead and follow the journey of this chlorine radical through the atmosphere. Well, that chlorine radical may then immediately try and interact with the closest molecule, which might, for instance, be ozone if it's up in our ozone layer. Ozone has a bit of a weird bond. For those in HL, you know this to be resonance. For those in SL, you generally just refer to it as a single bond and a double bond. Either way, we can see that the bonds in ozone, specifically this bond or these resonant bonds, are not as strong as that double bond between oxygen and oxygen. This creates a target for the radical to kind of pounce on. So what it will do is it will go ahead and attack those weaker bonds, trying to form its own covalent bond, and it will succeed, creating ClO radical plus oxygen. Now, this ClO radical will continue with its own little bit of mischief. And because it's a radical, it's very reactive. It will react with maybe another neighboring ozone, creating now Cl radical and two oxygens. What you'll notice is that we actually end up creating more chlorine radicals, which can start this process all over again. These radicals wreak havoc in our ozone layer as they continue to turn ozone into normal oxygen, which, while very breathable for us, ozone is important at blocking ultraviolet radiation from reaching Earth, causing increased temperatures and melting of our polar ice caps and even higher rates of skin cancer. So it's very important that we don't get these radicals released into our atmosphere. So basically, we can simplify this by saying radicals break down ozone in a self-propagating reaction, maybe even chain reaction. One of the things that you'll note, as I mentioned earlier, is that we don't really have them interacting with these with just this double bond, meaning that they're not going to interact with oxygen. The radicals are always going to prefer those weaker bonds, and they actually are unable to break that oxygen-oxygen bond. So one of the last things that we're going to end on is part of 3.3.2, which is what is this called? Well, simply we call this initiation. Initiation is basically the homolytic process, homolytic fission that leads to these further processes. So when we see homolytic fission that leads to further radical propagation, we call that initiation. A note about initiation as well, just to finish this video off, is this is always endothermic. That ultraviolet ray must be absorbed, that energy must be absorbed for that bond to break. So I hope this helped you learn a bit more about radicals, and have a great day.